Hey everybody, and welcome to Calculus. This video lesson is going to cover the definition of continuity of a function at a point. And through this activity, we're going to explore the different kinds of discontinuities that can exist in functions, and we'll also look at the formal way we prove that a function is continuous at a point. So to begin, it would be important for us to maybe make a sketch and write down the phrases or the names of the various kinds of discontinuities that we'll see in functions throughout calculus. And the three types are removable, jump, and infinite. And those three types of discontinuities can be distinguished by the three corresponding features that we might find in the graph. For example, a hole in the graph would be associated with removable or removable point discontinuity. A piecewise function where there's a break or a step, we'd call that jump discontinuity or step discontinuity. And then if we have a vertical asymptote within the function, we would have infinite discontinuity as represented by that vertical asymptote. So on this paper here, we're going to look at the formal definition of what it means for a function to be continuous at a point. We'll just call it x equals a. These three conditions must be met. All three criteria have to hold in order for this function to be continuous. The first one is we have to make sure that the function value f of a exists. We need to have a function value that exists. The second one is that the limit from the left and the limit from the right as we approach a also exists and that they match, which implies that the limit overall as x approaches a exists. And then the third component is that the first two values must be equal. The function f of a has to equal the limit as x approaches a of f of x. And if all three of those conditions are met, then we can prove or we can verify that the function is continuous at the point x equals a. So I wrote that again in the way of a formal proof down below here. So I would maybe say Roman numeral 1, show that the function exists. And Roman numeral 2 is the trickiest one. We need to have all these different pieces and components of limits and proper limit notation throughout our proof. Begin by showing that the limit as x approaches your number from the left and from the right both exist. Bracket them together and show that they're equal, which means that the limit overall as x approaches that value exists. So there's a lot to kind of show in that second step. And the third and final step, does part 1, your value from part 1, equal the value from part 2? And if they do, that's your third and final step. Now remember that continuous functions can be kind of described graphically as being able to draw the function with your pencil or your pen or your marker and never, ever picking up your pencil off the paper. If you can do that, if you can make such a sketch or a drawing and you're always on the paper, then you have a continuous function. But if there's a hole or a vertical asymptote or some kind of jump where we would have to lift our pencil off the paper, that would be cause for alarm, especially if we're trying to examine for continuity at that point. Now, here's the first example. Number 1 says determine if the function f of x equals 1 over x is continuous at x equals 2. So let's examine what the limit is as x approaches 2 from the left of 1 over x. Here's the picture. As I approach x equals 2, it appears that I'm approaching 1/2. As I approach x equals 2, or as I approach 2 from the right, I'm climbing to 1/2. So the two one-sided limits match. What about the function value itself, f of 2? Does f of 2 equal 1/2? Sure enough, it does. Now, the question says, is this function continuous at x equals 2? Well, the answer would be yes. But when the word justify or prove or verify, when those words come into play, then we've got to get very specific and use our formal definition of continuity at a point. So here are the three criteria, and let's follow along as we kind of make sure that we have them all written down. So jot this down. Number 1, f of 2 equals 1/2. State that the function exists and what the function value is at the point x equals 2. Now all the limits. Be very careful with the limit notation. The limit as x approaches 2 from the left of f of x is 1/2. Below that, write the limit as x approaches 2 from the right of f of x also is 1/2. And then I like to bracket those two together because those two limit statements lead me to state the next one, which is this, that the limit of as x approaches 2 overall of f of x exists and is 1/2. And it's really that key component that we want to go after. And then third piece, don't forget to end with this, that the function f of 2 and the limit as x approaches 2 of your function both equal the same value. In this case, they're both equal to 1/2. And because they're equal, we can conclude that the function is continuous at x equals 2. It's very specific, very formal, and all of those components must be present whenever you're asked to write a proof or to verify the existence of a continuous function at a given point. Now, consider the same function, but let's now move off of x equals 2 and let's go to x equals 0. In problem number 2, notice we have a vertical asymptote right here at x equals 0. So the limit as x approaches 0 from the left, if I travel left toward 0, we're actually falling to infinity, so negative infinity is where that limit is going. The limit as x approaches 0 from the right would be climbing forever to positive infinity. And then f of 0 is undefined, so I don't have a value. Is this function continuous? Well, we would say no. This fails. Part 1 fails. I don't have a function value at x equals 0. F of 0 is undefined. And the left and the right sided limits also don't match. So we kind of fail this definition all over the place. We would conclude by writing that the function is not continuous. Justify according to the definition of continuity. You could simply say any one of those two reasons, show why part 1 or part 2 fails, and that would be all you would have to do to prove that something is not continuous, that a function is not continuous at a given point. Now, a word of warning, be careful with piecewise functions. Problem number 4 in this activity presents a piecewise function defined as cosine of x, which is continuous across its domain, and then x squared plus 1, which is also continuous across its domain. But because they're broken up at this point x equals 0, I have cosine defined less than 0 and x squared plus 1 defined greater than 0. We don't want to automatically assume that just because we have a piecewise function, that means the function is not continuous. With a little exploration here and a little examination of the limits from the left and the right side of 0, we can find that actually the limit does exist and they're equal, and the function f of 0 also exists and equals what the limit value is. So number 4 would be a continuous function at the point x equals 0. And I've justified accordingly here with my 3 criteria for that formal definition. Now, there's one last example I'd like to talk about with you. And this would be an example that you may find on an assessment, on maybe an AP exam review, or a multiple choice question at some point. It's a piecewise function that's broken here at x equals 2. And the problem is asking us to use one-sided limits to find the value of the constant k that makes this function continuous at the breakpoint or at the transition point. The key phrase right here is to use one-sided limits. The very first step you need to do is show with proper limit notation what is going on as x approaches 2 from the left of my function, and then what is going on as x approaches 2 from the right of the function. So begin by writing that statement. The limit as we approach 2 from the left must equal the limit as we approach 2 from the right. This statement must be in your work in order to earn full credit, especially because the directions are asking us to use one-sided limits. Let's now get more specific. Well, as I approach 2 from the left, I'm on the x squared plus 6 piece. So let's examine the limit as x approaches 2 from the left of x squared plus 6. And we'll equate that to the limit as x approaches 2 from the right of kx plus 1, where k is some unknown constant. And by the way, we're setting these two equal to one another because in order to have continuity, the left and the right-handed limits must be equal. That's where we get the equation from. And now that I'm ready to evaluate each one of these limits, I'm going to use direct substitution on either side, plugging in the number 2 in for x. So let's see what we get here. 2 squared plus 6 must be equal to k times 2 plus 1. I evaluated the limit. Let's continue to solve our equation. 4 plus 6 is 10. Subtract 1. And it appears that our k value will be equal to 9/2, or 4.5. So if you plug in 4.5 for k into our piecewise function, we will have a continuous function at the transition point of x equals 2. We could confirm that value of k by graphing. And to prove it, here's the proof for continuity. Checking 3 components. Number 1, f of 2 exists. F of 2, if I plug in 2 into my function, is equal to, remember that k equals 4.5, so 4.5 times 2 plus 1 is 10. The limits as we approach f of x, or sorry, as we approach 2 from the left and the right, those both are equal to 10, meaning the limit overall as x approaches 2 is equal to 10. The function value at 2 and the limit value as we approach 2, both are the same, both equal 10. Make sure you state that as the third and final component to prove continuity of that function at the transition point. So that's what continuity of functions is all about in calculus, and that's how you'll use the formal definition of continuity to prove and explain and verify whether or not you have continuous pieces of functions at those given points. I hope that was helpful for you. Good luck in the rest of your continuity proofs.